Hello, everyone. The topic of our lecture today is search. Basically, we are going to learn about the structure of the most common search algorithm in artificial intelligence. We are going to discuss their time complexity, their space complexity, uh, their completeness, and their optimality. Search algorithm can be divided in two categories. The first category is uninformed search. In this category, the search algorithm does not have any prior information about the solution. And the second category of search algorithm are informed search algorithm. In this category, the algorithm will be provided some prior information or estimate about the final solution. Under uninformed search category, we are going to study depth first search algorithm, breadth first search, and uniform cost search. These are the topic of our lecture today. So next lecture, we are going to learn about informed search algorithm. Basically, we are going to learn about greedy algorithm, A+ search, and graph search algorithm. In this lecture, after we learn about the structure of the three most common uninformed search algorithm, we are going to analyze their time complexity. Basically, we want to know how much time does it take for the algorithm to run or process the data to find the final solution. And we also are going to take a look at their space complexity. By space complexity, we refer to the amount of the memory that the algorithm need to store the state of the search problem. And we also are going to take a look at this algorithm in terms of completeness. Completeness refers to the state where the algorithm is able to find a solution at the end or not. Disregard of the optimality of the solution. We just want to know if there is any solution in this state if the algorithm is able to find that solution. And finally, we are going to analyze the optimality. By optimality, we kind of refer to the performance of the algorithm in terms of finding a best solution, or in case of search algorithm, for example, pathing, finding a shortest path. Okay, so let's get started. We start the lecture by defining a search problem. Basically, a search problem consists of a state space. The state space refers to a set where in this set we have all the possible cases that the search problem can be in. For example, assume that we are working on a search problem for a Pac-Man game. And in this game, the number of grid is basically a square of 3 by 3, where at this location of this grid, there is a dot food that the Pac-Man will eat by each move. So here we have shown some of the state that the Pac-Man can be. In here, Pac-Man is located at the center of the square, where it could be considered as the starting point. Here also is another starting point for the game. And finally, these two can be a final state that the Pac-Man can be, where he can, I mean, he eats all the food dots in the space. The second features of a search problem is a successor function. Successor function basically tell the search problem how to move from one state to another. And when you do this, what are the actions and costs associated with that? For example, Pac-Man right now is located at the corner of this game board. So Pac-Man can have two different states when by taking two different actions. For example, it can move to the north, which is going to cost the algorithm by 1 if they assume that each move going to cost 1, and the dots food at that location will be eaten by Pac-Man. Therefore, the representation of the food from 1 changes to 0. Therefore, if Pac-Man chooses to go to this route, then these are the actions and costs associated with the successor function. Pac-Man also can move, from this state to this state by moving to the east. If it does that, then the cost associated with that is 1, and the food at that location will be eaten by Pac-Man, and therefore it's represented by a 0. And each search problem has a starting point or starting states, as we mentioned at the beginning. So these two states, for example, can be a starting point for Pac-Man or search problem for this specific search problem. Also, a search problem consists of a goal test. By that, we mean that the goal test is a condition that exists in the search problem where you basically understand if you are at the final state or at the solution node. So we will see an example about this just in a few slides. And a solution to a search problem is a sequence of actions which transform the start state to a goal state. For example, for this specific problem, our start state in here, then the Pac-Man can take a sequence of actions to finally arrive at this state. So the sequence of all those actions, which we can be defined as a plan, is basically the solution for this problem. One thing to note is that search problems are modeled. For example, in the previous example for the Pac-Man with the grid of 3 by 3, Pac-Man basically evaluate all those possible actions and come up with the plan to eat all dot foods in the game board. Search problem are models in the sense that we cannot basically create a real world problem completely because of the resource limitation that we have in our computational devices. So our model could be an accurate representation of the real world problem. So as the accuracy of the model goes up, then the complexity or the resource needed for that model also increases. And if you can represent a real-world problem with a good accuracy, then the solution that probably we will come up with gonna be an accurate solution for that given problem. But if your model is somehow underrepresented the real world problem, then the solution that you come up with may not be the optimal solution that you are expecting. We will see an example of this in a few slides. Let's start explaining the search problem with this example. So we call this example traveling in Romania. This example actually comes from the textbook that we introduced for this course. So the objective for this basically search problem is to find a path between the city of Arad here to city of Bucharest in Romania. Let's see what the state space is for this search problem. So the state space for us are the cities that somehow represented by this map. Successor function for us in this case are the roads. So basically the roads connect two different states to each other, and the successor function is move from one city to adjacent city, and the cost can be the distance between two cities. And then how about the start state? This example, in this example, the start state is very obvious. So we are going to move from the city of Arad to Bucharest. Therefore, our starting state is city of Arad. How about the goal test? The goal test, as we explained, is a condition that there's some sort of question that specify whether we are at the destination or at the goal or not. So in this case, this is the goal test. Is state equal to Bucharest? How about the solution? Well, the solution are basically a combination of different cities starting from Arad to Bucharest. For example, it could be Arad, Arad, and then Sibui and Vargas, and finally Bucharest. So this is the solution for this specific search problem. Basically, this could be a solution. We don't know whether this is optimal or not. Let's take a look at another example and see what are the technical terms in search problems. In search problem, we have the notion of the word state. Word state basically include every last detail of the environment. For example, for this Pac-Man game with this grid size, the word state basically include all the dot foot location and the Pac-Man location and the detail for the walls and obstacle in this game board. A search state basically is a subset of the word space of the word state. We only keep the detail that we need for our planning. Basically, we do some sort of abstraction. So, depending on the problem, then the search state for a given problem could be different. For example, if for this word state, we can define two different search problems. So the first one is the padding problem. In padding problem, the state for us will be X and Y location of the Pac-Man. For example, we assume that the location of the Pac-Man is in here, and the goal destination is here, and for us is the only thing that is important is the location of the Pac-Man that could be represented as an XY set. Then the actions associated with this search problem can be only going to north, going to south, east, or west. So we are not consider any diagonal move for this given problem. Then the successor function for this problem is to update the location of the Pac-Man after each action. And the goal test is this one. Is X and Y the end location? For example, for this given problem, assume that the end location is in here. So at each given state, we can ask this question to see whether we arrived at the solution or not. The second problem that can be defined for this given with this game board in the top can be the problem of eat all dots. Basically, what we mean by that is for the Pac-Man to eat all of these white dots in the game board, and finally, we end up with no food dots in the board. So what do you think about the state in this situation? Is it the XY location or something else? So the state for this problem, in addition to the XY location of the Pac-Man, is also dot Boolean. So the state is a set of the location of the Pac-Man, and if that dot Boolean is present at that given point in the board or not. Then action could be the same, so Pac-Man can move in 4 different directions. Again, here we do not consider any diagonal move from Pac-Man. And the successor function is to update the location of the Pac-Man and possibly update a dot Boolean at that given location. The goal test here in this search problem is different. So in this search, we only care if there is any food left on the game board or not. So basically, we want all these dot food will be eaten by Pac-Man. So that's the goal for this game. At this point, let's talk about the state space size. To discuss this, let's consider a simple Pac-Man problem with this dimension, when the Pac-Man can move between these dot foods in the space. And as you can see from here, the Pac-Man can be at this location when it's moved, can be at this location, this, and so on. So when you add this up, the Pac-Man can be at 12 location vertically, and it can be at 1, 2, 3, 4, 5, since we are considering the location between them. Also, the Pac-Man can be at 10 different locations horizontally. Therefore, agent position or Pac-Man position is the multiplication of 10 by 12, which is 120. And then we also care about the food count. We want the Pac-Man to eat, for example, all these dot food on the game board, and we have about 30 dot food in this game board. Therefore, we also need to consider all those 3D.food in the game board. We have two ghosts in this game, and these two ghosts each can be at 12 different positions. And the other things that we care about is the move or action by the Pac-Man or the facing of the agent, which is north, south, east, and west. So now let's consider the word state for this problem. So how many states do we have for this word state, and how much memory we need to have in order to store all those states in the memory. So this is the result. So we have the Pac-Man can be at 120 location as we calculated in here. And then we have dot food. Dot food at any given location could be present or not. So at each given location, we could have two states for two cases for the food. It is present or not present. Therefore, since we have about 30 dot food and each can have two different cases, then we are going to have 2 to the power 30 for the dot food on the game board. Considering the Pac-Man position and the number of cases that dot food can have in this problem, then these are the number of states associated with that. Since in this problem, we also have two ghosts, which each ghost can be at 12 different positions, then the number of positions that the ghost can be are 12 to power of 2. Therefore, we have to multiply that to the number of cases as well. The other important factor that is can be the determinant factor in this problem is the facing of the Pac-Man or of the Pac-Man, where it moves. So it could move to the north, to the south, to the east, and to the west. So it can have 4 different actions or facing. Therefore, these are the number of possible states that this game board can have. Now, depending on the definition of the objective for a given problem, then the number of states can change. Let's see what is the, if we consider the a padding search problem. For example, assuming that Pac-Man right now is at this location, and what if it wants to arrive somehow at this given location? So what are the number of different states that it can have? So as we explained above, agent position is 120. So for this problem, we don't care about dot food or the location of the ghost. What if we only care about the problem that defined as eating all dots? So for that problem, the Pac-Man location is important, and the existence or non-existence of the food dot is also important. So the number of states for this given search problem, therefore, is 120 multiplied by 2 to the power 30. So just to clarify, in these two problems, we didn't consider the existence of the ghost. All right, now consider this gaming board when we have 3 ghosts, and then we have the Pac-Man itself, we have the dot food, and in here we have a new component here called the power pellet. Power pellet is a kind of food for the Pac-Man. So when Pac-Man eats that power pellet, then it gets strong, and therefore it somehow scare the ghost. So if the ghost comes in here, they change color and they cannot kill or eat the Pac-Man. So for this given problem, then how many state space we can have, and how we can specify them. For this problem, so the agent position is important for us. So X, Y location, the dot Boolean, I mean the small dot Boolean are important. The power palette Boolean, the big one, are also a contributing factor to the number of states. Also, the remaining scared time. So when Pac-Man eats any of these power pellets, it is going to get stronger, and there is a timer associated with that. For example, Pac-Man can stay in that strong position for like 3 seconds. So within these 3 seconds, if it hits a ghost, or if a ghost approaches the Pac-Man, it cannot basically kill the Pac-Man or eat the Pac-Man. Therefore, the time duration is also a determining factor for the number of states for this given problem. As you can see here, number of states could be very, very large. Okay, now let's take a look at the state space graph and search tree in search problems. In a state space graph, basically we develop a mathematical representation of a search problem. We have a notion of nodes that are abstracted from the word configuration, and we have arc that kind of represent the successor function or the actions between nodes. And then the goal test also is present in the state space graph, which can be a set of goal nodes or possibly only one node, depending on the underlying search problem that we are studying. So if we consider the previous example for a game of Pac-Man with 3x3 grid, then the state space graph could be something like this. So this is going to be our starting nodes. Then from here, we could have 2 different states. So these are our arc. So Pac-Man could move to the north and go to that state, and this could be another possible state. And one thing to note is that in a state space graph, each state occur only once. For example, here we have a state that can be the result of this state when the Pac-Man move up, or could be the result of this state when the Pac-Man move down. So for the state space graph, each state happen only once. So we do not create something similar in here. We only create one state, and if that state is a result of like several other nodes, then we connect to that node using this arrow as represented in this example. Therefore, using the state space graph, we avoid repeating the nodes or states. In practice, we can rarely build a full graph in memory. But theoretically, knowing that it's a useful idea. As explained before, we only keep the amount of the part of the graph that we need for our search problem. Now, this is another state space graph. In here, assume that the starting point is S and the goal point, that destination is G. And these are the nodes of this problem. And these are the actions or the arc that connect different nodes to each other. Okay, now let's take a look at search trees and see how they are different from state space graph. So basically, in search trees, we make the tree using what if questions. So for example, we start from this state and we say, what if we move to the north by 1 and it's the dot at that location? Then we come to the next state. And then the other possible move for the Pac-Man could be move to the east with cost of 1 and eat the dot food at that location. And then we end up with this state. So at this state, then we could also have a set of different actions. So in this state, the possible number of action is moving to the north, moving to the east, and moving to the south. Therefore, we branch out to 3 different states. For this as well, we branch out to 3 different states. And we continue until we reach to the end state somewhere in here, for example, where all the dot have been eaten. For this problem, for the search tree representation, we can have repetitive states, but in the state space graph, as shown before, we don't have repetitive node or repetitive state. That's the difference between them. One thing to note in here that we call the start state in the search tree as the root node. And the resulting node or the state from the root node or the other node called the children of the node. For example, here, this state is the children of this root node. And if we create another state that comes as a result of this node, then this node can serve as a parent node for these new, basically, children nodes. So these are the children nodes. Okay. All right. For most problem, basically, we do not need to build the whole tree. You will see this, as we explained, the 3 uninformed search algorithm in this lecture. Now consider the state space graph that we have in the previous slide. So this one, so where the starting state is S and the final destination is the G state for us. So we can build a search tree, as we said, using what if question. So we start at the S or root node and start saying that, okay, so what if we move, for example, in this direction? Then our child node could be D. What if we move to this direction? Then our child node could be E. And then what if we move to this direction? Then the child node could be P, for example. And then if we expand each of these 3 nodes, then we end up with this search tree where the G state or the final state appears in 2 different node location in our search tree. But as you can see in the state space graph, G or the final destination only shown only shown once. All right, so let's have a quiz and consider this 4-state graph for this quiz. And let's see how big is going to be our search tree. So you can pause this video and draw the search tree for this 4-state graph. Okay, if you are done that, let's do this with each other in here. So we start from node S, and then the possible transition from S could be to node A, and the other possible state could be node B. Once we are at node A, we have also two possible, we can have two possible outcomes. One could be B and one could be G. And once we're at B location, we also have two possible outcomes. We can go to A and we can go to G. So if we go back to A, then from B and expand B, from B again we can go to A and we can go to G, and then expand again, then we go to B, and so on. And this continues until somehow infinity, because we have a loop in our state space graph. So the question is, how big is this search tree starting from S? And the answer is infinity. So this is the way that we basically expand this state space graph. So as you can see, there are a lot of repeated structure in the search tree. Okay, so let's now take a look at the search example, our previous search example, where it was traveling in Romania, and see what is going to be its search tree. This is basically, this one can serve as the state space graph. But what if we want to draw the search tree for this given problem? So we start from city of Arad, and the possible outcome or possible state from the successor function in this problem could be three different cities. We could go to Zarind, we could go to Sibui, or we could go to Timisoara. And then we can start expanding from the left, expand this one, and then this is one of the possible outcomes. Then we can go back to Arad, and so on. So let's take a look at the search tree for this one. So we start with the city of Arad. It's going to be our root node. And then from there, as you can see from the graph, there are three different possibilities. And each of these can be expanded again. So again, Sibui can be go back to Arad, we can go back to Fagaras, and we can go to Oradio, and we can go to Remisiu, Vil, Sia. So this is easy to expand the search tree. So while we are expanding each node, the children of that given node, basically we refer to those children as a fringe of the given node. So for example, in here, this is the fringe for our root node, and these four cities are the fringe for the parent node Sibui. So in search problem, we try to expand as few nodes as possible, because expanding node and then maintaining those in our search problem require a memory space. So if I can design a search problem that require less memory space, we somehow save in the memory and the resources. You will see we will be having a comparison between these three uninformed search algorithms in this lecture regarding the state space or memory size. Okay, so this is the way that we expand that state space graph. Now, let's take a look at the general tree search algorithm. Basically, any general tree search algorithm can be represented using a function. So we can say tree search, and there are going to be two arguments for that tree search. So first we need to define the problem. For example, for the Pac-Man problem, one of the problem could be padding, and the other problem could be eating all food. And then we need the strategy to kind of solve this search problem. And then the outcome of this function could be return a solution or a failure as a result. So now let's take a look at how we actually write the function for a given search tree. We do the initialization of the search tree first. So we define the initial state of the problem, and then we are going to have a loop where these actions are going to be repeated over and over, and we only exit when the certain criteria are met. For example, if there are no candidates for expansion, then return failure. So this is where we actually go through all the nodes in our search tree and didn't find any solution so far, and there is no node left to actually expand. So at this position, we say that, okay, we expand all the nodes and we didn't find any node that kind of represent our solution. So then the failure gonna happen. But if there is some candidates, then you choose one of the leaf or children, and then you expand that children according to a given strategy. Okay, the strategy for us in this lecture could be depth first algorithm, breadth first, or uniform cost search. And then we expand it, and then we say if the node contain a goal state, then return the solution. If that children node is like our solution, that's our goal state, we return the solution. And else, if it's not, add the resulting nodes to the search tree and repeat this loop until the end. So important ideas for the search problem are the fringe. So you need to know the notion of the fringe and the expansion, exploration strategies. The main question in search tree is which fringe node to explore next. So these are the main question for each different strategy, as you will see in the next few slides. Okay, consider this problem, this state space graph, and then we want to basically draw the tree search in this problem and arrive starting from the location or state or the root S and ending up with node G. Okay, so we start our search from node S, and then we expand it. So there are three possible nodes for the three possible children for this starting state. So D, E, and P. So let's draw those. So we show them SD as an SD, SE, and an SP. And then we need to choose one of these states and expand that. Okay, if you look at the graph, then what you will expand? Since we have a visualization of the search tree, we may choose to expand node E. But if we follow a given strategy, because we don't know in a big graph, we don't know which nodes are closer to the destination, so we have to come up with a strategy. So assume that we choose the leftmost node, then we expand that. So basically, we choose SD and expand SD. Now we can cross off SD from here and add those three children to our what's called the table. Then we are at this location. So if we stick with our strategy where we wanted to basically expand the left node, we should start from B. But again, since we have visualization of the search problem, assume that we go to location E and start expanding that node. So then the next node that we are going to expand is going to be this one, SDE. So once we expand SDE, we come up with SDE H and SDE R. So these are the two possible outcomes for that. And then in here also we can choose either H or R for our search path. So let's choose R and expand SDER. So once we expand SDER, we get rid of this and then we write down the possible outcome for that. So we can have SDERF in here, and that's the only outcome coming up from node R. And then at F location, we can move to two different nodes. We can move to G and we can move to C. Therefore, if we expand that, then we can have two different states in here, SDERFC and SDERFG. So if we choose to expand G, then we somehow arrived at our destination, and the path that we come up with is this path. But you may ask, is it the optimal path or not? We don't know that because we need a strategy to test that. But since for this given problem, we have a good visualization of the whole problem, we somehow use this information and come up with this path. But in practice, you need a strategy to basically search the tree. So here we choose kind of the random strategy to move along different nodes. So this is the whole tree that, as you can see, this is the word state that we didn't draw. We didn't draw it. We only draw the part of the graph that we needed in our strategy. And here's the visualization how we moved from S basically to the destination. All right, now we saw that how we can expand a search tree and how we can come up with the path for that given search tree. Now let's learn about some algorithm and see how we can systematically solve a search problem. So the first search problem that we are going to discuss is a depth first search. In a depth first search, basically, when you want to expand the node, you need to have a strategy to do it. For the example that we have done, we kind of use our visualization, information that we have from the graph, and we somehow expand the node. But in practice, when you want to do this systematically, you need to have a strategy. So one of the search algorithms that provide that strategy for us is depth first search. Basically, in depth first search, you choose the deepest node to expand. So you stick with this plan and then you expand your search tree until you reach to destination. Let's see how we can do this. Okay, starting from node S, then we have three possible, outcome from this state. We can go to D, we can go to E, and we can go to B. So let's take a look at the depth. So in here, the depth of the node D is somehow 1. The depth we can define as a distance from the starting or the root node. As you can see from here, D, E, and P, all of them have the same depth of 1. Therefore, since they have a depth 1, then we can choose to expand the leftmost node always. If we arrive at the situation when all the nodes has a similar depth, then we could consider to expand the leftmost side node. So in here, according to this strategy, we are going to expand node D. So We expand D, and then under D, we are going to have again B and C and E node. And the other possible node to expand are E node in here and P node in here. So as you can see here, the depth of P is 1, depth of E is 1, depth of E at this location is 2, depth of C is 2, and depth of B is 2. But we said that whenever we firstly consider the deepest branch or deepest node, so in this case, the deepest node are these three nodes, B, C, E, and once we find that, and there are several of them, we stick with the left side node, and this for this example is node B. Therefore, we take node B and expand that. And then we left with node A. Node A is kind of the end node in here because there is no possible action that we can take from node A to arrive at any other node. Basically, the arrow shows that the node A only is a receiving node and there's no output from it. Therefore, this is the dead end for us, and we don't consider that in our expansion. So again, we come back and we take a look at the depth for each of these nodes. So we're done with B. Now we have node C with depth 2 and node E with depth 2. So we consider these two. And then we stick with our strategy that we always choose the left side node to expand. In this case, we expand node C. As you can see from here, from node C, we only have one possible outcome, which is A. Again, we end up with A, and A is an impasse. Therefore, we go back and check the possible node that we can expand. We have node E here, basically at this branch with depth of 2. We have node E at this branch with depth of 1, and P with depth of 1. Therefore, we choose node E to expand. Then the outcome of node E could be H and R. So H and R has depth of 3, but we say that we stick with the left side node, the most left side node, and this, in this case is H. We therefore expand node H. Once we expand node H, we come up with P and Q, both with depth of 4. And as you can see, we have these two nodes for expansion. We have node R with depth of 3, and we have node E and node P with depth of 1. Therefore, we stick with the plan when we choose node P to expand. Therefore, the next one going to be P, and then we expand Q. Q is the basically impasse. There is no way out from it, and therefore we go to node Q. And node Q also, again, here in this branch, there is no way out. Therefore, we go back with to the deepest node in our table, which in this case is R. We expand R. There is only one outcome from it. Then we go to node F with depth of 4. Therefore, we're going to be expanding that. And then we expand F. There are two possible outcomes, then C and G. We stick with the left one. We expand C. We arrive at A, and A is an impasse. Therefore, we go back to the deepest node, in this case, which is G, and expand that. And if we choose the goal test and do that, we know that G is our final destination. Therefore, we choose these routes in our search problem to arrive at node G. So as you can see from the previous example, this is kind of the path that depth first search algorithm take. They just take one branch and they go down until they reach the destination. Sometimes they reach the destination, and sometimes they do not, and then therefore they come back, and again then they try second time, and possibly they could get to their destination this time. Search algorithm properties. So as explained at the beginning of this lecture, we could have we have the notion of completeness. We say that the algorithm is complete if it's guaranteed to find a solution if one exists. And we say that the algorithm is optimal if it is guaranteed to find the least cost path or the shortest path in our search problem. The other features of the search problem that we can consider is time complexity. How much time does it take for the algorithm to run to find the solution? And the other feature or other factor or parameter that we need to consider for any given search problem is the space complexity. Basically, how much space do we need to store all those states in the memory? So you actually saw that in the previous depth first tree problem, so how we keep track of the nodes and their depth in the memory. So we keep the nodes that we have expanded, and we keep also the depth of those nodes in the memory when we do the expansion. So let's take a look at the cartoon of a search tree. We start from a root at the top, and then we go down until we find the solution. Assume that our search tree has a branching factor of b. For example, in average, you have b number of branches that comes out from your given state. And then maybe if we start from the root node, the number of nodes appear at each layer is like this. So at layer 1, we have only one node. Layer B, we have b nodes. And in layer 2, we have b nodes. And in layer 3, we have b multiplied by b node, which is basically b square node. And this goes on until, if we assume that we have m number of tiers, then the number of available nodes in our search tree could be the summation of all these nodes, which is 1 plus b squared plus bm, and that has a complexity of OBM. The solution could exist at different depths in our search tree, and it depends on the algorithm, how it performs and which solution it could find. So right now, if we consider this image for our depth first algorithm, the solution that we come up with may not be the optimal solution. So we talk about number of nodes in the entire tree. It's a summation of the nodes at each layer, and it has a complexity of bm. So as we talk about this, our depth first search algorithm, so the number of nodes that we expand in the tree, we only expanded the deepest node. Therefore, we somehow go down in this direction without expanding the other nodes in our search tree. So let's see how many nodes we expand. So this is the way that the depth first search algorithm progress. It takes the left prefix of the tree always, and if it finds the solution, that's fine. If it does not, it start moving to the right until it finds the solution and declare that one as a goal test, and it stops. So as you can see from here, this node is closer to the root node, and basically that could be the optimal solution. But our depth first search algorithm find the node that is a bit further away. If in the depth first search tree, if you are unlucky, you may expand the whole tree. For example, if the solution is at this location. Therefore, it depends on where the solution is, the number of the nodes that you expand. If therefore m is finite, the number of layers that we have, then in terms of time, it takes the of BM, meaning that even if the node is in here, since we have to move, B layer, in average it could take O of BM time. And how much space does the fringe takes? It is the summation of the previous node that we stored in the memory. Basically, we go to the deepest node. So we start from here. We have this at the memory. So B1 is at the memory now. We move to the next layer. Then we have B, the B number of nodes in the memory. Then we move down. So at this point, we have only one. Therefore, when there are, and assuming that there are B nodes for each expansion, then therefore we are going to have M number of B nodes for our siblings. Therefore, the number of siblings is the OBM. Is the question you might have, is this search algorithm complete or not? And the answer is that if M is somehow finite, then we can say that it can be complete. And then is it optimal? Then the answer is no. It only finds the leftmost solution regardless of the depth or the cost of the node as represented by this graph. The second category of the search problem is the breadth first search problem. So in this search problem, we expand the shallowest node. So let's take a look at this strategy. So we start from S, then we have D, E, and P, each with the depth of 1. Then which one we are going to expand? Again, we choose the left side node to expand, since they are all equal. Then we have expanded D, so now we come up with B with the depth of 2, C with depth of 2, and E with depth of 2, and then we have E with depth of 1 and P with depth of 1. Therefore, since we want to choose the shallowest node, we have to choose something between E and P, and since they have the same minimum depth at this point, again, we choose the strategy of expanding the left side. Therefore, we choose the node E. And then we come up with 2 other nodes. And this time, H has a depth of 2, R has depth of 2. Therefore, then we have node P with depth of 1. So consider comparing this, all nodes, the shallowest node is P. Therefore, we can expand P. And now we come up with the node Q again with depth of 2. And if you take a look at all these nodes, they have the same depth. And therefore, again, we stick with our initial plan and expand in the left side node, which in this case is B. We expand B, we come up with A, and A gonna be having a depth of 3. Therefore, we go back and expand C, and then we come up with A. And we repeat this process until we find the solution. And therefore, our solution in this case is going to be this path from here to S. Okay, now let's take a look at breadth first search problem properties. What nodes does BFS expand? Basically, expand the shallowest node, and this is the way it progresses through the search tree. Therefore, it finds the shallowest node at the top of the search. Okay, So now let's talk about the time complexity and space complexity of the brief first search algorithm. So as you can see here, the number of nodes that this algorithm expand is starting from node 1 plus b squared until bs. Therefore, it's the order of bs. And then how much space does it take for the fringe? Uh, that one also is OBS. So the time taken is OBS, and the number of nodes that we need to save in the memory also are order of BS. Okay, is the algorithm complete? That answer depend on whether the number of uh, the number of S, whether it is finite or not. If it is finite and the solution exists, then the answer is yes. And is it optimal? Uh, the answer is yes if the cost from moving from one node to the next one is 1, or basically all costs associated with the successor function moving from one state to another state are equal. This may not be clear at this point. We will see clarification on this point when we talk about uniform cost search algorithm. Okay, this is somehow a representation of these two classes of algorithms. So this is the depth first algorithm. It takes one branch and expand it until it reaches to the end of that branch. And the depth breeze first search algorithm is start expanding the shallowest node, and it moves like that until it's find the solution. All right, now let's take a look at an animation of the Pac-Man game and kind of guess what algorithm we actually use to implement this game. So let's take a look at the first one. Okay, one explanation about this is that so this black wall in here are the obstacles. So when the Pac-Man, for example, wants to move from this location to the destination location defined in here, it cannot pass this black wall in here. And here we assume that there's somehow all these space are covered with somehow water. And then in the few next example that we are going to have, we are going to have a notion of shallow water and deep water. For this problem here, we assume that the depth of the water is equal at all kind of location in the game board. So let's play this one again and see if this is a depth first search or breadth first search, considering all those points. As you can see, the algorithm expanding this way, somehow equally in all direction. Therefore, so once it expands that in the memory and come up with the solution, then the agent is going to take this path to the destination. As you can see, somehow the nodes have been expanded uniformly from the root node. So they start expanding uniformly from the root node, and that tells us that this algorithm is breadth first search. Now let's take a look at this example. So as you can see in this example, let's run it again. As you can see, the algorithm does not expand from the root node equal in all those directions. It's basically take the deepest branch first, and if it is unsuccessful, it's going to return and expand the other nodes. So since it takes the deepest branch, therefore this algorithm is depth first search algorithm. So let's take a look at this quiz and compare DFS with BFS. And the questions are, when will BFS outperform DFS? So in what kind of situation B's first search algorithm could outperform DFS, whether in terms of time complexity or space complexity? And so the other question is that when DFS outperform BFS? So to answer this question, we can take a look at the graphical representation of the search tree that we have before. So in here, somehow we know that if the solution exists at the shallow branch, then basically the algorithm that's going to outperform is the Breeze first search algorithm. And if our solution exists at somehow the deepest branch or farther away from the root node, maybe the depth first search algorithm is the better choice. And the other thing that you might consider is the fringe of the search problem. So if, for example, the fringe of the algorithm is somehow narrow, I mean the search problem is somehow narrow, then it might be a good idea to use the breadth first search algorithm. And when it is somehow it has a wide fringe, as you can see, if you use the breadth first search, then it's gonna take a lot of space. Therefore, it might be a good idea to use the depth first search algorithm. So these two can be a determining factor. How deep is the solution, and what is the branch factor in this algorithm? If the branch factor is low and the solution is at the near to the root node, then possibly using the breadth first search algorithm is a better idea. But if the fringe are big or the branching factor is large, then it might be better to use the depth first search algorithm. Okay, now there is another technique that combines somehow iterative deepening algorithm. Is kind of a combination of the breadth first search and depth first search algorithm. And the idea is this: run a DFS with depth limit of 1 first. So basically, you use the depth first algorithm, but the depth that you consider for that is going to be with the limit of 1. If the solution exists, it's fine. If not, this time you consider the problem with a depth limit of 2, and then run the DFS algorithm. If the solution is there, it's fine. If not, this time you choose a depth of 3 and run DFS algorithm. And finally, you may come up with answer. So isn't that wastefully redundant? So at the beginning, it might seem that the algorithm is somehow redundant because it has to resume searching from the root node after each iteration. For example, when you run it with limit of 1, the solution is not there, then you have to run it with depth 2 and then again search the whole space, and then if not there, then you make the depth of 3 and then the whole space, and not there, for example, in this given problem with the depth of 4, and finally to find the solution. A computer simulation showing that if the computer experience shows that it is basically not a bad idea to use the iterative deepening. And the reason is that the most work happens in the lowest level search, and therefore it is not that bad. Okay, cost-sensitive search. As explained, BFS finds the shortest path in terms of number of actions, and it does not consider the least cost path. We now are going to take a similar approach and consider the least cost path in our search algorithm. So the uniform cost search. Then we have the notion of uniform cost search at this point. So now consider the state space graph that we have before, and this time you can see the cost associated with transition from one node to another. For example, if you want to move from S to D, the cost is 3, but if you want to move from S to E, the cost is going to be 9, and when you want to move to S to P, the cost is 1. This algorithm, uniform cost search, is going to take the cheapest path in the search tree. Let's start the algorithm. So at S, so the cost basically is 0, then you are going to expand S, and while you want to expand that, you just take a look at the cost and see the node with the cheapest cost is P. For example, in this case, we have 3, we have 9, and we have 1. P is the cheapest, therefore we expand node P. And then now we have the cost of 16, we have cost of 9, we have cost of 3. Therefore, the next node to expand is D. We expand D, now we have cost of 4, and then we have cost of 11, and we have cost of 5. All right, so if you take a look at node B, right? Node B is in here, but the cost associated from node D to B is 1. But by cost, what we mean is the cost from the source somehow to the current state, which is the summation of 3 plus 1, which in case is 4. Therefore, if you take a look at the existing node that we haven't expanded, we have node B with cost 4, C 11, E 5, and then we have node Q with cost 16 and node E with cost 9. So the cheapest node in this case is going to be node B. Therefore, we expand node B, and then the cost going to be 6 for that node A, and then the next cheapest node going to be node E at this location. So if we expand that, we come up with node H and R now with cost 13 and 7. So now we have 7, 13, and because 6 is the terminating point, we do not have any more further expansion for that. And then we have now 11, we have 7, we have 13, and we have 9. And the cheapest one this time is going to be R. And you continue this process until you reach the destination, which in this case is G. So if you consider the layers in terms of cost, so we have layer of cost 0, for example, then we have layer of average cost of 1, like that. And as you can see, the layer are right now uneven in terms of the space, but are kind of uniform in terms of cost. Okay, now let's take a look at the features of uniform cost search algorithm. What node does UCS expand? Basically, expand the cheapest node first. So here is the cost. If the cost is less than 1, then we expand that. Cost less than 2, cost less than 3, for example, like that. And then we basically find the solution with the cheapest cost here. And all right, so as explained, if the solution cost, for example, is C star, for example, as this location, this one is C star, then an arc cost as at least epsilon in average, moving from one layer to another layer, then the effective depth is roughly the cost in that layer, for example, in here, divided by the epsilon, which is the average of the cost from moving from one layer to another. Therefore, we are going to have almost C star over epsilon layer in the uniform cost search algorithm. Time takes to expand this search tree until to reach the destination is the exponential O of b to the power C star by epsilon. Is somehow similar to B's first search algorithm. How much space does the fringe take is again O to the power B, O of B to the power C star over epsilon. And then is the algorithm complete? And the answer is assume the solution has a finite cost and minimum cost are arc is positive, and the answer is going to be yes. So is it optimal? The answer is yes, and we prove this as one of the special case of a star search algorithm in the next lecture. So what are the costs associated with uniform cost search algorithm? So UCS explores increasing cost contours. So the good thing is that UCS is complete and optimal. And the bad thing is that explore option in every direction. It's like somehow similar to the Breeze First search algorithm. So it's actually followed same strategy, but this time it considered the cost to move into those all direction. And the bad thing is that it uses no information about the goal location. So as you can see, it's uniformly expand to the goal. And so we are going to fix these issues in our next lecture when we talk about informed search algorithm. Let's take a look at the demo of the empty UCS. So when there is no wall or no obstacle. So uniform cost search expanded uniformly around the root node until it basically reaches to the destination. So these are the contour that it takes. Okay. Now, let's consider this problem. So in this problem, we have two different level of waters in our game board. So the blue part are the water with the deepest level, and the light blue have the less actually depth. Therefore, cost of moving from here, for example, to the destination, if we choose the lowest depth water, it's going to cost less. So basically in this simulation, the cost of moving one location in the deep water is 3, while moving into the shallow water, the cost of moving one position is 1. Let's see how different search algorithm is going to reach to the destination in this scenario. So you need to guess in this demo which algorithm we are running to reach to the destination of the red square at this here from the green one. So as as you can see here, somehow the nodes are expanded uniformly from the root node. And the algorithm does not much care about the cost of expanding node when it reaches in here. Therefore, this is not a UCS. This is also not the deep first search. And most probably this algorithm is DFS, since it expands in all directions regardless of the cost to it. Okay. Now next video. So let's see which algorithm is this. So as you can see here, the algorithm somehow avoid to enter to the deep water. So it somehow chooses to reach the destination from the shallow water. And therefore, this algorithm is UCS. And the last one. As you can see here, the algorithm also doesn't care about the cost. It expands the deepest node first. Therefore, this algorithm is DFS. As you can see from the expansions of those algorithms for the search tree for all these three algorithms, all these algorithms can be implemented using the same strategies, and the only different thing that these three algorithms have is the way that we come up with the child nodes. So therefore, we can frame all these three algorithms as one algorithm and use different kind of expansion to differentiate between them when we are implementing them. As we said, search algorithms are the model. So the agent doesn't actually try all the plans out in the real world. So it basically simulates all those possible states and then take action when it's find the optimal solution or the solution in the search problem. Okay, so we talked about the model of a search problem, and we said that whether we reach the destination or not, it depends on how accurate our model is. So right now, take a look at this example. For example, you run a search algorithm and it says that, okay, move from this purple road until you get to the destination end. And then when in practice to come and arrive at this street, Loma Vista here, then you'll see that it is a narrow path and you can basically drive from here. Therefore, your model did not accurately represent the real world scenario. And also here is the other case where the search gone wrong. So basically, you could go from here to here directly and not taking this path. This is where you actually model your search problem in a wrong way. So this is the end of this lecture. In next lecture, we are going to talk about informed search algorithm and heuristic search, and see how we can tackle some of the issues that exist with uninformed search algorithm. Thank you.